So let's look at our final subtopic in motion in two dimensions, momentum in two dimensions. And I'm going to start off with an introduction to momentum. Some of you last year would have done a reasonable amount of stuff on momentum. I know others of you may not have done so much on momentum. So I'm really just going to review initially some of the basic concepts about momentum before we get into what's in the course this year in terms of momentum in two dimensions. Again, why are we looking at this? Why is this important? Well, hopefully by the time we finish this, you'll understand why conservation of momentum is probably the most important conservation law in physics. It is the law and the theory that lets us understand what happens in collisions, explosions. It's also very important in terms of rocket propulsion and spacecraft propulsion and that sort of thing, and how we work out how they work and how we either alter orbits of satellites or how we send spacecraft out to deep in space. So let's get into it. So what is momentum? I think the best way to think of it is as a measure of how hard it is to stop an object. So if you want to have a picture in your mind of what momentum is, think of it as how hard it is to stop an object. And obviously, the greater the mass of a moving object, the harder it is to stop. If you've got a car coming at you at 100 kilometres an hour, that's going to be easier to stop than a truck coming at you at 100 kilometres an hour, because the truck has a greater mass. The greater the speed of a moving object, the harder it is to stop as well. So it's going to be much harder to stop a car coming at you at 160 kilometres an hour than it is a car coming at you at 60 kilometres an hour. The greater the speed, the greater the momentum. So if we think about that mathematically, momentum, we give momentum the symbol P. M had been used for too many other things. The units for momentum are either kilograms meters per second or sec newtons. I think as we go on, you'll see why we use sec newtons. But both of these units are acceptable and they are equivalent to each other. So momentum is equal to mass multiplied by velocity. Obviously our velocity needs to be in our standard units of meters per second and our mass in our standard units of kilograms. So this is how we calculate momentum. Obviously the greater the mass, the greater the momentum, the greater the velocity, the greater the momentum. But I think the picture in our head of what momentum is best described by what we've got up here at the top of this. So why is momentum so damn important? And I think the reason it's so important is it's always conserved. And because it's conserved, it lets us analyse and find lots and lots of useful information about collisions, about explosions, and in a sense I mentioned before, propelling rockets. Well, basically that's just a controlled explosion that we're using to accelerate a rocket or a spacecraft. So, but in terms of analysing collisions and explosions back in terms of what happens, say in a military sense or in a car accident and all that sort of thing, conservation of momentum is a law that is really going to let you get into, analyse and explain those questions. So I'm just going to have a look here using my two little Pasco cars on a little low friction track at some of the sort of scenarios we can sort of picture in terms of momentum. Okay, so let's use these motion carts here to look at some of these things that I was just talking about. So just thinking about momentum firstly, hang on, I've got a guest appearance. Pepper, you can't be in this video. Goodbye. Okay, so firstly, thinking about what momentum is, and this idea it's a measure of how hard it is to stop an object. So firstly, this blue car here, we're basically just using this to measure how hard it is to stop. So the further this car goes, the more work was done in stopping this car. So it's a measure of how hard it is to stop the red car. So firstly, I think I talked about, obviously if we've got
a small amount of mass, a smaller velocity, that car stopped fairly easily. If we increase the velocity, so the greater the velocity, the greater the momentum, the harder it is to stop something. So we saw that there was more work required to stop that. Secondly, we talked about mass. So if we have a car with a lighter mass colliding, that's easier to stop. It's not as hard to stop. If we increase the mass of this car, these masses reach 250 grams. The car weighs 250, so we've basically just tripled the mass of this car. If we hit it with the same speed, see the blue car moves further. It was harder to stop. So the greater the mass, the greater the momentum, the greater the velocity, the greater the momentum. In both cases, the greater the momentum, the harder it is to stop an object. Now let's look at conservation of momentum. Firstly, let's consider a couple of simple collisions. These are just collisions in what we call one along a line, so one dimension. It's a bit harder to simulate two dimensions. So, basically in a collision, momentum will be conserved. So if these two cars hit each other head on doing the same speed and they stick together, basically the momentum of the blue one will be going this way, the red one this way, they cancel each other out, and that basically they both should come to a stop. And they almost do, I just didn't quite get it right. So that, if you like, is a simple collision. We could also look if the red car is stationary and it gets hit by the blue car. The two cars move off after the collision with half the velocity, because the cars are the same mass, the total momentum must be the same, so basically the velocity of the combined cars is halved because this car's velocity was initially 0. So we call these inelastic collisions where they stick together. Looking at some, obviously now let's say these two cars collide, but the red car now weighs 3 times as much as the blue car, and they're going to stick together. Obviously the red car's got greater momentum, so it sort of wins the tug of war and it pushes the blue car backwards because of its greater mass. I guess we could show the collision, two cars. Now if the red car is going faster than the blue car, once again the red car wins, and that goes in that way. So the way we analyse all these collisions is using conservation of momentum. When we do some stuff later on the year on radioactivity and particle physics, it's quite interesting what happens when large and small particles collide. And we can simulate here. So now we've got what's called an elastic collision, so they're going to bounce off each other like that. And what you can see, if these move together both at the same speed, after the collision the blue car gets most of the velocity, so the blue car goes off very fast. The red car here almost came to a stop. And once again we can use what we're going to learn about conservation of momentum to describe that whole situation that happens here. Just briefly also to look at an explosion type scenario. So we can simulate an explosion in these two cars by bringing them very, very closely together, and this has got a spring in it that we can trigger, and we can see both cars moved off in the opposite direction with equal speed because their mass was the same. Let's now make the blue car much more heavy. So this is going to be, if you like, the heavy fragment after an explosion. This is going to be the lighter fragment. And we can see the lighter fragment shot off much, much faster. And once again, we're going to use conservation of momentum to explain what happens. We're going to do that though in 2 dimensions, not just 1 dimension along a line. But I think this hopefully gives you a good little picture of what's happening with conservation of momentum. Bye, Pepper.